Hello and welcome to part 2 of the MIT Integration B 2023 qualifier round. In this video, we'll be looking at another 10 exciting integrals. So without further ado, let us take a look at problem number 11. So right off the bat, we have a rather strange looking integral over here. We have definite integral and then we have this ugly looking expression here. So usually when we see a definite integral as well as an integration expression without a standard form, I think the hint is for you to study what this function looks like and to calculate the area under the curve. So to understand this function a little better, let us take a look at first how does mod x look like. So mod x quite naturally looks like this, right? And now let's see what happens if we add a copy of -1 and then take the mod of that. So we shift the previous function down by 1 and then we take the mod of that. So it looks like this, where this value here is 1. So let's now add another copy of -1 and see if we can find a pattern. So this time, we have the previous function with -1, and we take the mod of that. So if we first shift down the previous function by 1, it will look something like this. So if we take the mod, we are flipping up the two tiny mountains here. So this looks like this, where this value here is 2. So if we continue this pattern, as I think you will be able to realize that this function over here essentially looks like this. It's a series of tiny mountains. So if because 2023 is an odd number, it will look more like this graph here, where we start off with a peak. And then we have basically a series of tiny mountains until 2023. And then similarly on the other side, we have a series of tiny mountains until -2023. So essentially now we need to find the area from this part of the graph to this part of the graph. And you can very quickly check that this is basically 2023 copies of mountains, which has the area of 1 each. So the area under the curve is 2023. So that's all for problem 11. Hope you found that interesting. Let's take a look at problem number 12. So for problem 12, you have an integral here with trigo functions. And right off the bat, the power 6 looks scary. But we also have sine square and cosine square appearing. So I think the natural suggestion is try and make this part of a sine square plus cos square cubic function. So what you want to do is first we write sine square x plus cos square x cubed, where if we expand this, you will get sine 6 and cos 6. And then we need to subtract off certain terms to make sure we don't change the expression. So first, let's just copy down the sine square and cos square from the question. And then now let's make the necessary adjustments so that we get back the original question. So we have sine 6 and cos 6 as explained, and we need to minus away the in-between terms, which are sine 4x cos square x, as well as 3 sine square x cos to the power of 4x. And the reason why this is very useful is, firstly, you get rid of the power of 6. Secondly, sine square plus cos square is just 1. So it's just the integral of 1 plus. And now we take a look at what happens if we extract out the common copies of 3 sine square x and cos square x. We get 1, and then minus sine square x minus cos square x. And so the term in the bracket here is 0. So we are essentially only integrating 1 dx. And so the answer is just x. So a very cute little problem here. Hope you enjoy this problem as well. Let us now take a look at problem 13. So problem 13 is a neat problem. The key observation is essentially that this e plus 1 looks like it is obtained by taking some copy of x to the power of e plus 1 And then when you differentiate it, the e plus 1 comes down and you're left with x to the power of e. So let's see how this observation can help us. With this observation, what you want to do is, let's consider the e plus 1 part and the x part separate. So let's write it as two different terms. You have x times the rest of the expression, but we also have the e plus 1 part. So we separate the sum essentially. And the reason for this is so that, as mentioned, this expression here looks like it is from differentiating x to the e plus 1, right? But at the same time, what we notice is that this expression here actually can be combined into just x e plus 1. And hey, x e plus 1 looks familiar, right? It is what we have just differentiated here. So this suggests that if we just look at the product rule, we get the answer, because indeed, if we differentiate this squiggly underlined term here using the product rule, we first get one copy of the first term times differentiate second term, which is still e to the x itself. And then we differentiate the first term, which indeed gives this, times e to the x. So indeed, this is the final answer. So a very neat problem that uses the inverse of the product rule. So let's take a look at problem 14, which is actually the hardest problem in my opinion in the entire question set. So for this problem, we have the integral from 0 to 1 of the sum of two terms, neither of which look like it can be easily integrated using standard techniques, especially the term under the square root. That is really difficult to integrate. So if they give you a sum of two terms, there must be a reason for doing so, because it doesn't quite make sense that they want to test two integrals in one problem. That is basically cheating. So how could the two parts of the sum possibly be related? Well, we have a square term here and a square root term here. So could it be that they are inverses of each other? So let's check that out. So if you write y as x squared over 2 minus x squared, and we want to calculate the inverse function, basically we write x in terms of y. Right, so we have 2y minus yx squared equals x squared, and we collect the copies of x on one side. 2y equals y plus 1 x squared. And indeed, we see that x is equal to square root 2y over y plus 1, which has the exact same functional form as the one given here. So what this means is that the two terms, one of them is fx, the other one is f inverse of x. And so now we use the property that fx and f inverse of x are reflections around the line y equals x. So if we have the graph of fx looking something like this from 0 to 1, then what we have is that the function f inverse x will look something like this. It's the reflection about the line y equals x. So the area under the curve is the area under here, as well as the area given by the horizontal shading. But because of the reflection property, this double shaded part is actually the same area as the unshaded part here. So the area is actually just the area of the entire unit square, which is 1. So by using the reflective property of fx and f inverse x, it doesn't matter what the graph looks like, we can very quickly conclude that basically the area of the curves after adding together is equal to 1. So this was not easy to discover, but hopefully you enjoyed the problem as well. Let's take a look at problem 15 now, which is actually quite instructive. So for problem 15, you realize that if we differentiate the bottom, you will indeed get a constant term as well as a x to the power of 2022 term, but the coefficients are wrong. So why not try and adjust for the coefficients to make them correct? So we have 1 plus 2023 x to the 2022 minus 2021x to the 2022. And the reason for doing this is that the top remains unchanged, but now we can split the top into something that is the derivative of the bottom and an extra term. So the first part of the integral can be easily evaluated. This is just the ln of x plus x to the 2023. Right? And then right now we minus the integral of 2021 x to the 2022 over x plus x to the 2023. So it looks like we didn't make much progress because the bottom is still x plus x to the power 2023, which is quite hard to integrate. But we can cancel a common copy of x. And so what do we get? We have ln x plus x to the 2023. And if we cancel a copy of x, we actually have x to the 2021 over 1 plus x to the 2022. So now the top, if we differentiate the bottom, we will just get x to the 2021, which is good, but the coefficient again is wrong, but that's easy to fix. We want 2022 in front. So what we do instead is we multiply and divide by 2022. So this is quite a standard coefficient adjusting technique. So now we have ln x plus x to the 2023 minus 2021 to the 2022 ln 1 plus x to the 2022. So if you want, you can even take out a copy of x here and then combine the x plus, or rather 1 plus x to the 2022 with the expression here, but it's not necessary. Regardless, this is the final answer, one of the forms of the final answer. Hope you enjoyed this instructive little problem over here. And let us now take a look at problem 16. So problem 16 looks like a rather strange looking trivial integral, but actually the trick is to not be scared away by the weird looking numbers. Indeed, this part here is simply a standard sine function which can be easily integrated. And this part here is the product of two trivial functions for which we know how to integrate, because there's a standard technique to this, which is to use the sum to product formula. So if you recall sine A plus sine B, this is actually 2 sine A plus B over 2 cosine A minus B over 2. So if we use the inverse of this, essentially the sine of some x times the cosine of some y is the half of sine of x plus y plus sine of x minus y. Okay, so if we apply it to the bracket part here, this is basically half sine of 43x plus sine of minus 3x. Okay, and the sine of minus 3x, this thing is actually just minus sine of 3x. So this means that the integral itself can be decomposed into a very standard string of trivial functions. So it's just 3 over 2 sine of 43x, and then minus 3 over 2 sine of 3x, and then we have plus 20 sine of 43x, which is making the whole thing here 43 over 2 sine of 43x. Okay, and so now this is just a usual trivial integral. This gives you minus half cosine 43x, and then plus half cosine 3x. So I hope you enjoy this nice little problem here. Let's take a look at problem 17. So problem 17 is really interesting because it has this weird looking infinite product here. So the key to evaluating this is to firstly, let's write out what this means. So this means 1 over 1 plus x times 1 over 1 plus x squared times 1 over 1 plus x to the 4, 1 over 1 plus x to the 8, and so on. And there's actually a standard way to evaluating such infinite products. There's a trick that you should know about, which is that any integer that is positive or equal to 0 has a unique way of being written in a binary expression, and conversely, any binary expression can be converted into an integer that is non-negative, right? So the way to express, when you expand this infinite product here, you can think about it as choosing either 1 or x from this term, then choosing 1 or x squared from this term, then 1 or x to the 4 from this term, and so on. And choosing 1 or x can be seen as choosing the digit 0 or 1 for the first binary expression. Choosing here can be seen as choosing 0 or 1 in the second binary expression. Here, 0 or 1 in the third binary expression. And the reason for this is as follows. Because let's say I choose x here, and then I choose 1 here, and x to the 4 here, and the rest I choose 1. What power do I get? I get the power x, and then so I get x to the 1 here, the contribution here, and then I get nothing here because I multiply by 1. Here I get the contribution x to the 4, and so on. So essentially, what I'm doing is my power here comes from a contribution of 2 to the power of 0. Do I have 2 to the power of 1? No. Comes from 2 to the power of 2. Do I have 2 to the power of 3? No, and so on. So in essence, the expansion here will give you all possible choices of the binary expansion in the powers. And so you will get all possible powers of x. So 1, x, x squared, x cubed, and so on. And you get it exactly once. So this is quite a common technique used to expanding infinite products of polynomials like this. And this expression basically is a geometric expression in the bottom now. So it's 1 over 1 minus x. So the whole infinite product just evaluates to 1 minus x. So the answer to this integral is the integral from 0 to 1 of 1 minus x, which is equals to half. So you hope you enjoyed this little problem here as well. And let us take a look at problem 18. So problem 18 is a bit tricky because the denominator looks like a nasty combination of e to the x and trigo, which doesn't have any standard formula. So what you might try and do is maybe we can put the top in the form of f prime x so that we can integrate the whole thing, right, as ln of fx. That's usually one way to deal with a nasty looking fx in the bottom. So with this inspiration in mind, let's see what happens if we instead differentiate ln of the nasty denominator. So let's try this out. This will give us a hint of how to adjust the numerator, right? So what is f prime? Over here, f prime is 2 to the x minus sine x plus cosine x. And actually at this stage, you might realize that you are actually going on the right track. And the reason for this is quite simple. How does the top and the bottom differ from each other? The top and bottom differs from the fact that you have a plus sine x versus minus sine x now. And so the difference is actually 2 copies of sine x. So this is 1 minus 2 copies of sine x over the nasty denominator. And this is exactly the integral that we want to work out, right? So this underlying part here is the integral that we want to evaluate. So this suggests that we can just rearrange the terms now. Sin x is, or rather sin x over the nasty denominator is given by half of 1 minus differentiating ln of this, right? That's sin x here. Okay, so, and of course we can integrate 1. So essentially this whole thing is what you get if you differentiate half x minus ln 2ex plus cos x plus sin x. And therefore the answer is simply given by this expression here. So that is all to problem number 18. Hope you enjoyed this problem as well. It's really a tricky little observation problem. And now we come to my favorite problem of the problem set, which is problem 19. So for problem 19, you have a very complicated looking expression, but the key to tackling this problem is to be clear-headed about what is behind all these confusing symbols. So first thing first, log pi e is basically a very lame way of saying log pi plus log e, right? And what's log e? Log e is just 1. So this is just a very confusing way of writing log pi plus 1, which by the way is just a number. So it looks very clumsy, but it's just a number, so there's nothing to be afraid of. And the top here can be written as log x minus log pi. And again, log pi is just a number. So let's see how we can simplify this integral over here, right? So if we break up the difference into two terms, we have log x, right, over log x to the power of log pi plus 1. And then I subtract log pi, which I emphasize again is just a number, over log x log pi plus 1. And you realize that once again there's another simplifying step we can take, which is this copy of log x cancels in one copy of log x here. So now we cancel that out. We just have 1 over log x to the power of log pi. Okay, now it looks slightly simpler, but it's still rather complicated looking. And this is where we need a bit of inspiration. We notice that we have this log x to the power of a number at the bottom. If we differentiate this whole thing, it will generate one copy. I mean, the power of this part will usually increase by 1, which is indeed the case we have for the second term here. And a copy of log pi might drop down, which is what we have in the coefficient here. So this is all very suspicious looking. So this leads us to investigate what happens if we differentiate 1 over log x to the power of log pi, right? So as I explained, you firstly get a copy of minus log pi coming down from the power, and then your power in the denominator increases by 1, so log pi plus 1 is now the new power, and then you need to differentiate log x, so you get 1 over x. So you almost got the second term here, except there's a 1 over x. So as before, this is actually similar to problem 9 in the previous video. What we want to do now is take a break, see if we can integrate the second term directly using what we have found in the parking lot. So I shall call this the parking lot expression. So it looks like we can almost integrate the second term because we have the antiderivative here, except for a 1 over x term. So let's try and integrate the second term. So indeed, the integral of the second term is what I have just written out here. But in order to use the antiderivative result, we had to introduce a copy of 1 over x. So I multiply and divide by x, right? So now that I've done this, I can now actually use integration by parts, because the part that is underlined here is in our parking lot. And we know what is the antiderivative. It is 1 over ln x to the power of ln pi. Okay, and then I multiply by x. And then now I minus the integral of the same thing, ln x to the power of ln pi, but I differentiate x, which is 1. And hey, this expression over here is identical to the first term in our question. So if we move to the left-hand side, what do we have? We have the required integral is essentially just the result we got from the integration by parts earlier. So it is just this. So this is a very nice little problem. It's similar in spirit to problem 9 in the previous video. So I'll recommend you to check that out if you haven't. So keep this technique in mind. And lastly, we have problem 20 here. So problem 20 is really interesting because it's just a polynomial, a definite integral. And so technically, given enough time, you can just brute force your way to integrate this polynomial and substitute in the endpoints and get the answer. But you're only given 1 minute per problem. So this looks like a time killer. And the way to do it swiftly is to rely on certain observations. So first observation is that the coefficients here are all powers, or sort of terms of the form n choose 5. Or rather, sorry, not n choose 5, but 5 choose k, right? So this suggests that you can write this in the form that has x plus 1 to the power of 5, which will take care of the first 3 terms here. And then you need to make some adjustments to make the other 2 terms come out properly. So you need to minus 2x squared, because you have 10x squared from this. And then you have 5x from here, so you minus 4x. And then you have a plus 1. So you need to minus 1. But instead of minus 1, I will instead minus 2 plus 1. And the reason for this is so that I can write this whole thing here again as a minus 2 of x plus 1 squared. So you see a lot of x plus 1s appearing now. And the reason why this is good is because your endpoints, your definite integral here, is symmetric about x equals to minus 1. See, it's a symmetric interval about x equals minus 1. So now we realize that x plus 1 is a symmetrical function about x equals minus 1 also. So this part here is an odd function about x equals minus 1. And this part is an even function about x equals minus 1. So when you integrate about a symmetric function about x equals minus 1, firstly, the odd function evaluates to 0. Secondly, the even function evaluates to twice a copy of, or rather, maybe it's simpler if I just write out first. This integral is just evaluated minus 2/3 y cubed evaluated from y equals minus half to half. And then this last term here is plus 1 because this 1 is evaluated across an interval of length 1. So it contributes an area of 1. And as mentioned, the thing about the even function is this thing is just 2 times the copy of minus 2/3 y cubed where y is evaluated at half, right? Because the even function, basically you have twice the area of the right side of the function. So you have this, and this evaluates up to something really quick, because you can cancel copies of 2 here, a copy of 2 here with 2 copies of 2 here. So you get minus 1, 2 times 3 plus 1, which is just 5/6. Yeah, so hope you enjoy this problem as well. It's really a time killer if you cannot find the quick observations that are needed. So that is all the integrals we'll cover from this year's MIT Integration B. Hope you enjoy the video. Stay tuned to the channel and see you soon.